from the third characteristic. Sir? Hello?
Can you move back before
Back
this slide?
this
Yes, thanks.
and
I just want to cap. So
oh.
done.
Don't worry about that, okay? It's already shown in the Microsoft team, okay? You can download them after my lecture. Okay? Okay, finish?
Yes, sir.
Okay? And after that, okay, you determine IL for time greater than 0 and IL for time less than 0. Both of them must be equal, right? The same quantity, IL, the inductor current. Okay? Okay? It means it must equal, but it equal only when time equal to 0. We take the third characteristic advantage from the third characteristic of the inductor. It is impossible to change the current through an inductor IL by a finite amount in 0 time. The inductor current for time less than 0 equal to 1.6 amp, and for time greater than 0, it equal to I naught e power minus 5t. Okay, both of them is equal. You set them to be equal. Okay, what happened? You can determine the initial condition that you cannot find from the second step, right? The second step is still have I naught here. In this step, okay, you substitute t equal to 0 or time equal to 0. Okay, anything power 0 give you 1. You can conclude that I naught equal to 1.6. After you get 1.6, yeah, you substitute them back in the general forms, the general solutions of the inductor current. You get IL equal to 1.6 e power minus 5t. Yeah. Now, if the questions ask you for the inductor current at time equal to 0.15 seconds, substitute them in this step. Okay, you get the inductor current at that time equal to 0.756 amp. Yeah. Now it finished. Okay. If the questions ask you for the other parameters, okay, in the first step, you must determine them. Okay. For time less than 0, you can determine them from the original circuit itself. Okay. But for time greater than 0, you must determine them from inductor current instead. Okay. Now I1 from the circuit shown in this figure, the switch is not closed yet, right? Therefore, the source is still supply the energy to all device in this case. Okay, the switch is still open. Okay, you can discuss the switch. Okay, and the inductor perform like short circuit for this step. Okay, now, okay, the current flow 2 amp flow in this point and split into, right? In the previous we concentrate on IL, but now we concentrate on I1, the current flow in the 6 ohm. I1, you can determine them by applying the current divider technique. Okay, I1 equal to 2 amp flow in here, split into, right? I1 equal to 2 amp, multiply with the resistance in another branch, okay? Multiply by 2 ohm and divide by the sum of all, okay? 2 plus A, okay? In this case, I1 equal to 0.4 amp, okay? Now, for time greater than 0, it's different. Time greater than 0, you must derive them from IL instead. Now, you check that. Okay, I1 is very easy. Okay, you can see that for time less than 0, okay, the switch is closed in here. It means it's no current flow in here. You can see that. If it's closed in here, no current flow in I1, right? No current flow in I1. Therefore, due to the short circuit of the branch, okay, therefore it's no current flow in the resistor. Okay, no current flow. All current will be flow in this part immediately. Therefore, I1 will be equal to 0 immediately for that step. Okay. Therefore, I1 at time equal to 0.15 will be equal to 0.2. You can see that due to when the switch is closed, it's here, okay, this part is already short circuit. No current flow in 8 ohm after switch is closed. Okay. Now for I2, the next step. The I2 is the current flow in the inductor. This case is a little bit, okay, you must, it's not simple, okay, because you can see that for time less than 0, it's easy. The branch is broken, right? The switch is open, therefore it have no current flow in I2. Okay, from the branch is open circuit, therefore I2 for time less than 0 is equal to 0. But for time greater than 0, yeah, you can see that For time greater than 0, okay, I2 will be composed by two current source, okay, yeah. When it short circuit here, you know that it have no current flow in the X ohm, right? You can discuss them. Due to the short circuit of the switch branch, no current flow in the 8 ohm. Therefore, at this point, I2 will be, you can write them in the form of, partial of them will be comprised by 2 amp source, okay? And another partial is came from IL. Therefore, in this case, at the top, at this node, okay, the current, okay, I2 equal to 2 subtract with, okay, IL. IL, you know about them, you can write them, okay, I2 is 2. Therefore, I2 equal to 2 minus 1.6 e power minus 5t. And in this case, okay, you can see that for this case, when the time is running, is okay, the power from the inductor will be depleted. When it's 0, okay, it means I2 will be equal to 2 amps, okay, because IL will be revert the direction of the 2 amp source, okay, and yeah, okay, I2 at the time equal to 0.15 equal to here. Now, in the overall point of view, okay, I will sketch 3 current for you to give you more understand. The inductor current, okay, for time less than 0, the switch is still open and the current 2 amp source, okay. 2 amp source is still charging to the inductor until it performs light short circuit, until it full charge. Okay, the inductor current equal to 1.6 amp. And for time greater than 0, okay, when the switch is closed, okay, the source is short circuit by itself, and it seems the source will be cut off from the inductor and the resistor in the right section. Therefore, in this case, the inductor current will be gradually drop and 0 soon. Okay. While, okay, at the first step and the second step must equal when time equal to 0, you can determine I0 at that step. Okay, and after that, okay, you can determine I1. I1 is the current flow in the resistor. Okay, for time greater than 0, it equal to 0.4 amp. And the time greater than 0 due to the short circuit part. Okay, the circuit is already bypassed this resistance branch and it will be 0 after that. Okay, for I2, the I2 is the current in the switch position. For time less than 0, due to the switch is still open, it's not closed yet. Therefore, it have no current flow in the broken bar. And when time greater than 0, the switch is closed and the short circuit, okay, the switch it jump to 0.6 or 0.4, sorry, 0.4 amp immediately and gradually increase, okay, by 2 current source, okay. One is from 2 amp source, another one from the inductor source, okay. And due to the direction is a revert and cancel the effect from each other, okay, will be increased and it reach to 2 amp source soon. Yeah, it's the overall of the example case, okay. From the final conclusion, okay, here, the inductor current must gradually change. It is possible to change the inductor current, okay. If the inductor current you plot, okay, it have some point that suddenly change, you wrong. Remember that you wrong. In the physics world, the inductor current cannot be changed suddenly, okay. But for the other, such as here, okay, such as the current flow in the switch or the current flow in the resistor can be changed suddenly from, okay, here from 0.4 amp to be 0 amp immediately, or change from 0 to 0.4, and after that it will be gradually changed. Okay, it's possible. Yeah, but for the inductor current, it cannot. Yeah. Now, in order to give you more understand, I will provide you more exercise. Okay, more exercise. Okay, for the circuit of the following figure, determine and sketch the capacitor current. Capacitor voltage. Sorry. Wait a minute. Okay. Yeah. Okay. Determine for the RC circuit in this case. Determine and the get the capacitor voltage, the capacitor current, and okay. Determine and get the the voltage at this point. Okay. The voltage across 400 ohm. Okay. And after that, determine all VC, IC, and the VO at the time equal to 1.3 milliseconds. Okay. For RC circuit, the first parameter that you must concern is VC. Okay. For VC, okay, you must compute VC for the time greater than 0 first and VT for the time greater than 0 in the second step. Okay. You determine the capacitance voltage. Okay. The capacitance voltage. Yeah. For time less than 0, the switch is contract in this position and it charge, okay, to this circuit for a long time. Okay. And we assume that any transient in the circuit died out long ago, leaving the purely DC circuit. The capacitor act like the open circuit to the DC current. Okay, it seems the branch is broken. What happened? You can see that this, okay, this voltage, okay, in the right hand side is not affects to the our interestings of the capacitor voltage. Okay, therefore we interest only in the left hand side part. Okay, in the left hand side, in this case, the branch is broken. Therefore, the capacitance voltage is equal to the voltage across 1250 ohm here. Okay, for here, okay, you know that it have two resistance. Okay, contract with the voltage source. Okay, it equal to 120. Okay, you can apply the voltage dividers. Okay, the voltage across 1250 equal to 120 volt. Okay, 120 volt. Multiply with 1250 and divide by the sum of them. Okay, 100. Okay, 1250 plus with 250. Yeah. Okay, give you 100 volt in this case. Okay, this for the capacitance voltage for the time less than 0. For the time greater than 0, what happened? When the switch is open, when the switch is open, you can see that, okay, the source is gone. Okay, the source is gone. When the source is gone, okay, the other resistance is here in this position. You must determine the equivalent resistance for this case. Two of them will be connected in series. Okay, you can see that two of them will be connected in series, and after that you parallel with 2K. Okay, after you determine the equivalent of this, okay, it will be series with 250 ohm and 600 ohm. Okay, and the finally is parallel with, okay, the final result will be parallel with 1250 later. Okay, from here, as okay, the equivalent resistance, if you compute them correctly, okay, it will provide you 625. The equivalent resistance is here, and the equivalent capacitance is already equal to 4 microfarad. Okay, multiply them, give you the time constant, and the general solution of the capacitance voltage equal to V0 e power minus t divided by tau. Okay, and the tau, so time constant equal to 2.5 milli in this step. Okay, at the first step, okay, VC equal to 100. Second step, VC equal to V0 e power minus t divided by 2.5 milli. Both of them is equal when time equal to 0. Okay, by the third characteristic of the capacitor, it is impossible to change the voltage across and capacitance. Capacitors we see by a finite amount in 0 time. Therefore, for time greater than 0, it's 100 time greater than 0. Okay, V0 e power minus t divided by 2.5. Both of them is equal. When time equal to 0, you substitute 0 in here. Anything power 0 give you 1. Therefore, you can conclude that V0 equal to 100. Substitute them back in the general form of the capacitance voltage. You get VC equal to 100 E minus T divided by 2.5 milli. Okay. And if the questions ask you for the capacitance voltage at the time 1.3 milliseconds, substitute them and you get here VC equal to, yeah, sorry, 1.3. Okay. Go to 59, sorry, 59.5 volt. Okay. And after that, if the questions ask you for the other parameters such as IC or the capacitance current, very easy. Capacitance current, you can derive them from VC directly. Okay, for both time less than 0 and time greater than 0. For time less than 0, okay, you know that, okay, for time less than 0, the capacitance voltage is a constant, okay, it fixed, equal to 100 volt, okay, therefore, IC or the inductor current equal to C dV dt. It equal to the time rate of change of the capacitance voltage, okay, and in this case, if the capacitance voltage is fixed, IC is 0.2. Okay, IC is 0.2. Okay, show you in here, right? Take derivative of 100, okay, constant. Now, for time greater than 0, for time greater than 0, okay, when the speed is gone is here, the same, okay. You can compute IC from VC directly, C dV by dt, okay. We don't care for the other part of the circuit, okay. If you can write IC in the term of VC. Wait a minute, sorry. A little bit earlier in this step. Okay, okay. IC equal to C dV by dt. VC equal to 100 e power minus t divided by 2.5 milli. Okay, you multiply them, differentiate EAT, give you A EAT. Okay, see here. Therefore, the final result, the capacitance current equal to minus 160 e power minus t divided by 2.5 milli. Okay. Yeah, and when the time equal to 1.5 milli, substitutes 1.5 in this step, you get that the inductor current equal to minus 95.12 milliamp. Yeah. In the overall point of view, okay, we know, okay, we know this, yeah, okay, VO, sorry, VO is the voltage across 400 ohm, okay, 400 ohm is, in this case, is here in the most left right hand. For time less than 0, okay, you can determine VO from the voltage source, okay, yeah, from the voltage source, you must use, okay, two step of the current the voltage divider. You can see that this, okay, the voltage divider separate them in two steps. The first one, the voltage across, okay, yeah, 600, and the voltage across the parallel result of the 2K and, okay, parallel with 500 ohm, okay, result equal to 400. Yes, 400 in this case. Okay, and now the V, okay, sorry, V4K, V2K. Okay, V2K equal to, we derive the first step in here. The voltage dividers, okay, the voltage across V, okay, equal to, yeah, 400, okay, divided by, okay, 600 series with the parallel, okay, and multiply with 120. After that, you use the voltage divider from, okay, after you know the voltage across 2K ohm, you use the voltage divider, split them between 100 ohm and 400 ohm, okay. VO equal to all voltage at the 2K ohm, okay, multiply with 400, okay, divide by the sum of them, 100 plus 400, okay. You get the voltage across 40 ohm by use two step of the voltage divider, you get 38.4 volt. And after that, okay, for time greater than 0. For time greater than 0, you must derive everything in the term of VC. Okay, it's considerably difficult in here because the VC is already in the most left hand. Okay, you know VC, or you know the voltage across here. Okay, across, okay, 1,250. Okay, you can the same, okay, you determines the voltage across 2K first, okay, by use the current dividers, okay. If you know the voltage across VC, you can determine, okay, the voltage of the 2K ohm, okay, by applying the voltage dividers, okay. Okay, the voltage divider equal to VC multiply with 2K and divide by the sum of them, okay, 2K plus 250 and 600 here, okay. After you get V2K, okay, you can determine VO. VO equal to, use the voltage divider again, okay. Okay, split, okay, the voltage across 2K, split into part. One is a voltage across 10 ohm, another one is voltage across 400 ohm, okay. Therefore, VO equal to V2K multiply with 400 and the sum of them, 400 plus 100, okay, give you here. Okay, you know, we substitute V4K and substitute them back for the VC, you get here. For VC, you know that the VC is, okay, equal to 100 e power minus t divided by 2.5 milli. This is the result, okay. And at the times equal to 1.3 millisecond, okay, VO equal to 2.5, 25.x, okay, e power minus 1.3 milli divided by 2.5 milli. And the final result equal to 15.2 volt. Okay, in the overall point of view, okay, the VC for time less than 0, okay, the switch is still contract to your circuit and drive it for a long time until it perform like short circuit. It equal to 100. And for time greater than 0, okay, you remove the sort. The current and the voltage will be dropped to 0 soon. It drop in the exponential form, okay, equal to 100 e power minus t divided by 2.5 milli, okay. And you determine IC in the form of VC. IC for time less than 0, due to the VC is constant, derivative of VC equal to 0. Okay. For time greater than 0, okay, you take derivative of the VC again. Okay. But in this case, okay, the result will be negative because VC is in the decaying exponential form. Therefore, the slope is negative. When you differentiate them, okay, give you the negative value, and we will be close to 0 again. Okay. Next one determines VO from VC. Okay. Determine VO from VC for the time less than 0. VO equal to 30x.4 volt. And for time greater than 0, it will be in the decaying exponential. But it must be jumped from, okay, 30x.4 to be 25.8 first. And after that, it will be gradually drop and drop to 0 soon. Okay. From this characteristic of the graph, you can observe that, okay, only the capacitance voltage can be gradually changed. It cannot suddenly change because if the capacitance voltage is suddenly changed, the current flow into them will become infinity. Okay, and for the other parameters such as IC, VO, or the other parameter can be gradually changed or suddenly changed. We don't care. But in this example, we will show you that IC and the VO will be suddenly changed too. Okay. I think I will provide you so many examples. Are you more clearly? Okay, now we can go to the next step. Okay. Okay. The next step is the unit step function, and okay. And for this lecture, okay, we will concentrate on the unit step function and the drive-in RL circuit. Okay, drive-in RL circuit. What about the unit step function? Okay, all first 4 topics that I teach it to you will be sort free. The sort free is mean the circuit used to drive by the sort for a long time. For time equal to 0, you turn off every sort. Okay, therefore the current and the voltage will be dropped to 0 soon, but it's not suddenly drop. It will be gradually drop. Sorry, it gradually drop. Okay, due to the capacitor and the inductor characteristic. But in this case, it changed. Okay, when time equal to 0, instead you remove all sort. No, you maybe remove some sort or maybe add some sort. The current and the voltage will be reached to a new value. Okay, not 0. Okay, maybe decreasing to some certain value or increasing to some certain value. Okay, before we concentrate on that point, okay, sometime, okay, in general, okay, we must define the mathematics function first to express that the switch will be turn on or turn off. Instead, we use the position of the switch like at the previous case. Okay. When we have been studied the response of the RL circuit and the RC circuit when no sort or no force function were present. And only this part we call them the natural response. Okay, it means the outputs or the response that depend only on the nature of the circuit. Any output or the response is obtained from the presence of the initial energy storage within the inductive and the capacitive element in the circuit. We have been solving the problem in which energy sources are removed from the circuit too. Okay, but in this section we must consider that type of the response which result when the energy sources are suddenly applied to the circuit instead. Certain special force functions which are discontinuous or have discontinuous derivative are called singularity. Okay, the singularity in this case, we have only two mathematics functions, the unit step function and the unit impulse function. But in this class, we concentrate only on the unit step function. The unit step function, okay, the symbol function is here. Ut equal to 0 and 1. Okay, it means it equal to 0 for time less than 0. And it equal to 1 when time greater than 0. Okay, it performs like the for time less than 0, the switch is already turned off. Okay, for time greater than 0, the switch is turned on. Okay, now if you activate the switch not time equal to 0, okay, maybe you can turn on or turn off at any time t0. Okay, the formula of the unit step will be can express in the more general case in the first equation. Therefore, the concise, the mathematical definition of the unit step function is here 0 and 1 here. But you can see from the mathematics analysis or the expression, you can see that the unit step definition never told you that, okay, what about the value between time equal to 0 or at time equal to 0? It told you that only for time greater than 0 or time less than 0, it equal to 1 or 0, okay? But at time equal to 0, in fact, it don't have any value between them. But even though the riser is not strictly at the part of the definition of the unit step, it is usually shown in each drawing. In the circuit analysis, a discontinuity or a switch action often takes place at instant that is defined at the time equal to 0. Okay, you see that we don't define them, but we physically draw them to contract, okay, to connect between two pieces of the graph to 1 and 0. Okay, in order to identify that this function is the same function. Okay, the same function. And in the physical sort and the unit step function, we will show you in here. In the unit step in here, you can see that in this case, the unit step is activated at time equal to 0.2 second. Okay, before the time equal to 0.2 second, the switch is still turned off. It means nothing in the circuit. Okay, but for time greater than 0.2 second, okay, the switch will be turned on. Okay, or you can use the switch will be show you in here. Okay, we have the switch in this position, and the switch will be activated at time equal to 0.2 second. Okay, now what about the response is? Okay, unit step is here. Okay, can I drink a little bit one? Okay, break 1 minute to drinking first. Sorry. Yes, I'm afraid that if I talk without drinking water, okay, maybe cause. Okay, now can we start now? Hello, are you here? Can we continue from the previous?
Yes, sir.
Okay. 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 You can see that by the unit step. Okay. The previous example or the exercise, we use the switch position in the second picture, right? In the B figure. Okay. In the picture B. Okay. But now, if you have the unit step, you can formulate them instead. You draw the switch. No, you can draw them in the normal sort. Okay. And the sort will be activated at the following mathematical form. it means for time less than 0, okay, the switch is not activated. And for time great, before the switch equal, before time equal to 0.2 seconds, the switch is not activated, okay. Time less than 0.2 seconds, the switch is deactivated, okay, and the switch is not activated yet. Therefore, it will be 0 volt, okay. But for time greater than 0, unit step equal to 1, right? If unit step equal to 1, it equal to multiply with 5, give you 5 volt activate. Or when the time greater than 0.2, the switch is placed in this position, okay. Therefore, the sort will be contract to your general network, okay. It's here, okay. Whether the question defines, whether the questions write in the unit step function or the switch will be provide you the same result, okay. And moreover, the unit step is one of the basic step function that you must study in EMAT and very powerful in about how to use them to model a complex signal, okay. Some very useful forcing functions may be obtained by manipulating the unit step function. Let's define the rectangular voltage pulse by following condition. Okay, you can see that the rectangular pulse will be 0, okay, for time less than T1, T0, okay, T0, and 0 for time greater than T1. Between them, it has some certain value. Provide you the rectangle shape. The rectangle shape will be expressed or can be modeled by using the unit step function, by use two unit step functions, subtracting at the different time shifting in here. In the physical point of view, what happened? The first term, it seems to be the pink sort is here, activate here. The second, the orange term will be the second sort in here. You can see that the direction of the sort will be reversed, okay. Therefore, the sum of them will be negative. The output equal to the voltage across them all, okay. You can see that for time less than T0, okay, T0. For time less than T0, both of these sort is not activated, okay. Therefore, nothing exists in your circuit. The first sort, the top, the pink sort and the orange sort is deactivated. Okay, now both of them, the sum of them or the multiplication, the subtraction between them, 0 subtract 0 give you 0. For time greater than T0 but less than T1, what happened? Okay, only the pink sort is activated. Only the pink sort is activated. The orange sort is not activated yet, okay. Therefore, if it activates only here, okay, we not subtract with the 0, give you we not, okay, give you the pink one, okay, give you the pink one, okay. For the last case, for time greater than T1, the time greater than T1, what happened? Both sort is activated at the same time, okay. Okay, the pink equal to V naught, the orange equal to minus V naught, okay. Both of them will be the same magnitudes but reverse in its side. The sum of them equal to 0. The sum of them is 0. Therefore, you can see that you can create the rectangle shape by using a unit step function, okay, by using a unit step function. Now, we will explain about the unit step function clearly. Now we go to the application. Why we must study the unit step mathematics function? Because we will use them in the driven RL circuit. Okay. For the driven RL circuit, okay, in this case, the driven RL circuit, we separate the computation step for the IL into 4 steps first, okay. Determine for if you can prove that, okay, observe the circuit first, okay, and if the circuit is the RL circuit, okay, you must determine 4 steps, okay. Determine the inductor current for time less than 0, okay. For that time, okay, we'll ring, okay, the equivalent inductor as the short circuit, okay. Due to the short circuit, the circuit is supplied by the DC source for a long time. The inductor perform like short circuit, and after that, using the DC analysis method to determine the inductor current. Okay. The second step, we determines the inductor current at time limit to infinity. Okay, when time equal to infinity. Okay, and the same. Okay, we assume that the inductor current perform like short circuit again. and you apply the DC analysis method to determine the inductor current. Okay, the third one, you can compute, the inductor current for time greater than 0 in the term of the time constant that compute from the equivalent resistor and the equivalent inductor with all independent source zero out. Okay, you kill every source during that time. How to kill the current source? You can kill them by open circuit, and you can kill the voltage source by short circuit them. Okay, find the time constant, and you can get the total response of the capacitance current equal to IL at time infinity plus with I hat e power minus t divided by tau. I infinity, the inductors at time infinity, you compute from 1.2 step. Okay, and okay. Okay, this from this equation that you compute from the 1.3 step, it have one unknown that you cannot compute in this step yet. Okay, and the unknown you can use 1.1 IL for time greater than 0, 1.3 IL for time greater than 0. Both of them, you can see that both of them will be the inductor current but different time. Okay, one is time for less than 0, one is time greater than 0. Both of them is equal when time equal to 0. And if you would like to determine the other parameters such as the inductor voltage or the resistance voltage, resistance current, or so on, derive them from inductor current. In order to give you more understand, I will provide you the example instead. Here in this case, we start by a simple one first. The unit step function, the source is not activated at time equal to 0. The source is activated at time equal to 3 seconds. 3 seconds. Therefore, this circuit will be the inductor and the resistor. Therefore, it's RL circuit. Checking that the driving source or not, you check at time infinity. When the time is when the switch is activated for a long time. The switch is here. The source equal to 12 volt. If the source is equal to 12 volt fixed, it means at the time infinity, it has some source that not 0. It's classified to be the driving source, the driving case, the driving RL circuit right in there. Now in this step, for the driving RL circuit, you must determine IL first. For the IL in this step, you have 4 main steps to compute the inductor current. The first one, the inductor current before the switch is activated. In this case, the switch is activated at 3 seconds, before 3 seconds. Before 3 seconds, it means the source is not activated yet. If the source is not activated yet, it means the current and the voltage at every point in this circuit is 0. Is 0. Now for the second step, you determine the inductor current at time infinity. At time infinity, the source is activated for a long time. It's not 0 anymore. And the inductors is driven by the source for a long time until it full charge. If it full charge, it performs like short circuit. We assume any transient in the circuit died out long ago, leaving the purely DC circuit. And the inductor performs like short circuit. Right, it's a short circuit. Therefore, if we short circuit in here, you can compute the inductor current very easy. The current V equal to IR, I equal to V divided by R. I equal to 12 volt divided by 1 kΩ. 1 kΩ. And after that, you get 1.1, 1.2. Now you get 1.3. 1.3 you require to determine the equivalent inductor and the equivalent resistor. But in this circuit, it's very simple. The equivalent resistor is 1 kΩ, and the equivalent inductor equal to 50 millihenry. Therefore, the time constant, the tau equal to L divided by R. You get 50 micro. The general solution of the inductor current will be expressed in this form: IL equal to IL infinity minus with I hat e power minus t divided by tau. IL infinity, you know, in the previous step, at the 1.2 step, equal to 12 milli. and the time constant equal to 50. Okay, every t you shift by 3 seconds. Every 3 you shift by 3 seconds. Okay, this is the general form up here, but in this step it's not finished yet because you have some unknown parameter. Okay, I hat is still unknown, and you can determine I hat from 1.1 step. For the 1.1 and the 1.3 is equal when time equal to 0. 1.1 is here for time IL for time greater than 0, it equal to 0. IL for time greater than 0 or before after the switch deactivate, okay, greater than 3 equal to 12 milli, subtract with I hat e power minus 20k t minus 3. Okay, both of them is equal due to the third characteristic of the inductor state that it is impossible to change the current through an inductor IL by a finite amount in 0 time. Okay, if both of them is equal, you can see that 0 equal to here, and this thing e power 0, okay, the time equal to 0, time equal to 3 seconds. Okay, anything power 0 give you 1. Okay, therefore you can conclude that I had equal to 12 milli. Okay, and you can get IL equal to 12, subtract with the 12, e power minus 20k t minus 3 milliamp. This is the general solution of them. If finished, no. The questions ask you for more. In this case, the questions ask you for VL. You can determine VL from the IL directly for both time less than 0 and time greater than 0. For time less than 0, the inductor current is 0 due to it have no source. Okay, no source generate or supply to any circuit. Okay, therefore it have no voltage too. VL is differentiate 0, give you 0. Okay, therefore VL equal to 0 too. But VL for time after the switch is activated. After the switch is activated, okay, VL equal to L di dt. Okay, but the inductor current equal to 12, subtract with the 12 e power minus 20k. Okay, and take derivative of the first term is constant, give you 0. Take derivative of the second term, e minus a, give you minus a, e minus at. Okay, but minus and the minus will be gone. Okay, you get here for the general solution of the capacitance. Yes, for the inductor voltage. Sorry, for the inductor voltage. Now, if the question is okay, yeah, in this case, in the overall point of view, what happened? The inductor current for time less than 0, it means no source is activated. Okay, for time less than 3 seconds, okay, no, nothing is activated yet. Therefore, the current and the voltage will be 0. Okay, at time equal to infinity, you know that the current will be reached to 12 milliamps soon. Okay, but the shape of the increasing is okay in the exponential form. Yeah. IL equal to 12 milli, subtract with I hat e power 20k t minus t. Okay, and 1.1 and the 1.3 is equal. Okay, therefore you can determine I hat from this step, and the I hat is equal to 12 too. Okay, 12 milli too. Okay, for time greater than for the other parameter that the questions ask you is VL, the inductor voltage. For the inductor voltage for time less than 3, you can see that due to the inductor current will be 0. Okay, its derivative will be equal to 0 too. Okay, and for time greater than 0, take derivative of the current. Okay, the inductor current. The first term is 0. The second term will be here. Take derivative of EAT. Okay, give you EAT. After you compute completely, you observe the graph a little bit one. You can see that the inductor current is always gradually change. It's impossible to make the inductor current to sudden change, because if you make the inductor current sudden change, the voltage across the inductor will be infinity immediately. Okay, when the input is changed a little bit one. Okay, now for the inductor voltage, and the other parameters, okay, can be saturation or graduation. We don't care for that, and no one can tell that for that circuit it must change suddenly or not. Okay, no, we don't care. Okay, only the inductor current can be sudden change, can be gradual change, cannot be sudden change. Because you may have the questions why the IL cannot sudden change. If the IL is sudden change, jump sudden change immediately, the voltage across them will be infinity at that point. If it have the infinity voltage or the infinity current at some point in your circuit, the circuit is broken. Okay. Okay, it's your turn. Okay. Hello, can you see the assignment, the quiz in the class?
Yes.
อาจารย์
Okay, capture it. Okay, I think it's okay. If you have some participant, it will be good. Okay, because if I talk, you maybe listen or sleep. I don't know. Okay, and maybe so tedious. Okay, now wake up and take the exercise. Okay, the time to take the exercise a little bit one. Okay, and I provide you complete solution in 15 minutes. Okay, I stop sharing the slide in 5 seconds. 4, 3, 2, 1. Okay, before that, okay. Before download the attendance checking, I would like to see your face now, okay? To identify yourself by open the camera now. Hello, Jimma.
Yes, sir.
Siri Pop. เห็นแต่ตาเลยโหซูมใกล้มากเลยเอง อัศมาใช่ไหมใช่ไหมไอ้หนู ธนายุทธโอ้โหนั่งออกแบบนั่งเป็นมิวสิกวิดีโอเลย Okay, if you don't have the camera, it's okay. Don't worry about that. Okay, okay, case by case. Okay.อ้าวชนนิการใช่ไหมรัจจา or right รัจจา
Yes.
Okay. Hello. Asika. Asika, right? Your name? If I pronounce them wrong, it's sorry for that. Okay. I tried. Okay. Good afternoon. ชนติใช่ไหมเอ็งอยู่ไหนเนี่ยในรถเหรอ
ครับ
ฮะ
เปล่าครับ ผมไม่มีกล้องติดกล้องครับ ผมใช้กล้องมือถือ
อ๋อ ใช้กล้องแฟนก็ได้ให้แฟนถือให้ หรืออยู่คนเดียว Hello อัศวิน Are you Thai or
ครับอาจารย์
Inter
คนไทยครับ
คนไทยใช่ไหมเพราะดูโอเคตั้งใจทำนะ จะได้ทำได้เวลาสอบ ธนพัฒน์ไงบ้าง
ครับผม
อันนี้ขยันอยู่จำหน้าได้ ตอนเรียนนี่นั่งข้างหน้า ไม่รู้เพราะขยันเพราะนั่งหน้าหรือว่าเพราะว่ามาทีหลังเลยได้เก้าอี้หน้า
ครับ
ตั้งใจดีแล้วพยายามทำดูนะ จะได้นั่น If you finish, okay, scan and okay, post them in the meeting chat. Okay, I will check that. Okay, it's right or wrong. If it's wrong, okay, you have the time to fix them first. Okay, before I provide you complete solution. Hello? Anyone finished yet? I give you another 5 minutes quickly. Hello? Anyone here?
Yes อาจารย์
Okay,
กำลัง
finish?
ทำครับอาจารย์
Okay. Oh, okay. Due to some of your friend is not finished yet, okay? I will provide you more time to do by yourself, okay? And the next time lectures, okay, before we start, okay, I will provide you complete solution, okay? I think if you do by yourself, you will more clearly understand what happened, okay? And the detail of them, okay? Or do you want to know about your solution now? Depend on you, okay? Okay, Jawad already finished? Hello?
Jan, did you call my name?
Finished? Hello? You already finished or not?
Not yet, Jan.
Not yet, okay? Nah. Okay, yeah. Therefore, okay, submit, okay, the next lecture time, okay? I will call to see about the solution and ask you for the, provide you about the complete solution, okay? See you next time. Good luck, everyone.
Yes, sir.
Thank you.
Sir. Have a good day, sir.
Thank you, sir.
You're welcome.
Thank you, sir.
Acha ครับผมไปได้ยังครับ